Welcome to this guided example on how to compare the performances of diverse electrical and combustion boilers. We have already studied the environmental performances in terms of primary energy, resource depletion, and CO2 equivalent emissions. We are now going to add investment and operational energy costs. Costs may be very country dependent and varies also quickly in time. Please be aware that the costs in this example are just used as an illustration and cannot be claimed to reflect current and local reality. Let's first summarize what we have learned this week in a flowchart. If we know the annual heating demand of a building and we know the conversion efficiency from final energy to energy demand, then we can calculate the final annual energy. I remind you that the final energy is the energy being delivered to the building either in the form of fuels or in the form of electricity or district heat. We have seen on an example that this conversion efficiency is close to 1 for electrical heating systems, but for non-condensing gas boilers it was 0.7. If we now know the conversion efficiency from primary energy to final energy, we can calculate easily the annual primary energy. I remind you that in our example, the conversion efficiency was 0.4 for Dutch electricity and 1 for gas, as gas is a primary resource. By combining the annual primary energy with the energy content of the fuel, the higher heating value, the annual quantities of fuels needed and therefore depleted can be estimated. By now combining the primary energy with the specific CO2 equivalent emissions, the annual CO2 emissions responsible for global warming can be estimated. We are now going to add the costs. Energy costs are generally expressed in an amount of money per kilowatt hour, just like on your energy bill if you have one. In this course we will express it in euro per kilowatt hour. So, by multiplying the final annual energy by the energy price, we know what are the annual energy costs. Finally, we have to look at the costs of the equipment, boilers in the cases we have studied. The prices are generally given per kilowatt, meaning that we need to know the nominal load to be able to calculate the investment costs. Investment costs are one in the time costs. It may be that high investment costs in efficient equipment are compensated by lower annual energy bills. That is why we prefer to express these costs in terms of yearly costs by dividing them by the service life of the equipment. Most boilers have a service life around 15 years, meaning that on average you have to replace them each 15 years. Finally, by adding the energy costs to the investment costs, we get the total annual energy costs. So in total we end with 4 annual performance indicators, the ones with a thick black outline in the flowchart: primary energy, resource depletion, CO2 equivalent emissions, and total energy costs. And to estimate these performance indicators, we need the energy demand from the building, data on efficiencies, heating values, and CO2 emissions, and cost data. As a last remark concerning the calculations of the CO2 emissions, we have seen that when dealing with electricity mixes, we will calculate the CO2 emissions with a slightly different method based on emission factors and final annual electricity use. In that case, we will generally not calculate the annual resource depletion as it is cumbersome if there are multiple fuels, but we will express it simply as primary energy. Our case will be the same building as in the MOOC energy demand in buildings. We simulated its complete energy use during a typical year, representative of the Dutch climate. In the present guided example, we are only interested by the space heating and the hot tap water. The data we need to calculate the performance of energy supply systems are the annual space heating demand, 854,052 kilowatt-hour, the hot tap water demand, which is 59,432 kilowatt-hour and is quite low as office buildings use little hot tap water. We also need the nominal power for space heating, which is 421 kilowatt, and for hot tap water, which is 17 kilowatt. Let's imagine that we want to compare the two following options. The use of a tankless electrical combi boiler connected to the Dutch electricity grid, and the use of a condensing wood pellet combi boiler. The price of boilers in the Netherlands is around €75 per kilowatt for an electrical boiler and 240 for a wood pellet boiler. Next to that, we pay 22 cents per kilowatt hour to the energy company for our electricity, and wood pellets cost 30 cents per kilogram. Because both options are based on a combi boiler, the same system and therefore the same fuels are applied for both hot tap water and space heating, so we don't need to make separate calculations. Let's start by the start. We just agreed to add space heating to hot tap water, by which the annual heating demand is 913 megawatt-hour. We switch from kilowatt-hour to megawatt-hour and round it up to avoid awfully long numbers. We have discussed in a former lecture that efficiency of an electrical instant boiler is 1. The final annual energy is of course electricity, and the amount of needed electricity is 913 divided by 1, which is 913 megawatt-hour. We now need to calculate the primary energy. For this, we need the efficiency of making electricity from natural resources. We saw that in the Netherlands, this efficiency is around 0.4. The annual primary energy is therefore 913 divided by 0.4, which is 2283 megawatt-hour. If we know the electricity mix, you can find it in a previous lecture. You can estimate the resource depletion for each of the fuels belonging to the mix. 59% comes from gas with a heating value of 9.8 kilowatt-hour per cubic meter, and 14% from coal with a heating value of 196 megajoule per kilogram, which is 82 kilowatt-hour per kilogram. We neglect the oil, and the remaining part is sustainably produced, and we assume the same efficiency of 0.4 for all power plants. This leads to the depletion of more than 137,000 cubic meter gas and 4 ton coal. Let's now look at the CO2 emissions through the emission factor of electricity, which is 0.46 kg CO2 per kilowatt-hour electricity in the Netherlands. The annual CO2 emissions are therefore 913 ton times 0.46 equals 420 ton CO2 equivalent. What about the annual electricity bill? Well, with a price of 22 cents per kilowatt-hour, we come to an annual bill of 913 times 0.22 equals 201,000 euros. And what about the investment costs? We saw that the nominal load for space heating is 421 kilowatt and for hot tap water 17. If you remember the working principle of the combi boiler, you have noticed that space heating switched off when hot tap water is needed. As the nominal load for space heating is much higher than for hot tap water, the 421 kilowatt will be enough for both. The investment cost of an electrical boiler were believed to be €75 per kilowatt, which brings us to the total investment cost of 421 times 71, which is €31,600. Finally, the service life of a boiler is 15 years. So the annual equivalent investment costs are 31,600 divided by 15, which is €2,107, by which the total energy costs are €203,107. So to conclude, with this electrical boiler, the building has a primary energy consumption of 2,283 megawatt-hour, emits 422 CO2, and the energy costs are a bit more than 203,000 euros. Let's look now at the condensing wood pellet combi boiler. Can we this time use the same efficiency for space heating and hot tap water? Well, we discussed in a former lecture that the condensing mode is not working with hot tap water because of the too high temperature. So we have to consider separate efficiencies. Let's take 0.95 for space heating and 0.86 for hot tap water. The final annual energy is therefore 854 divided by 0.95 plus 59 over 0.86, which is 968 megawatt-hour in the form of wood pellets. Wood pellets are, of course, primary resources. Therefore, the efficiency from primary energy to final energy is 1, and the annual primary energy is 968 divided by 1 equals 968 megawatt-hour. Let's now consider the energy content of wood pellets. According to an earlier lecture, it should be 16.2 megajoule per kilogram, which is the same as 4.5 kilowatt-hour per kilogram. The resource depletion is therefore 215 ton wood. Let's look now at the CO2 emissions. We saw in a former lecture that the Dutch government considers the emissions to be 0.014 kg CO2 equivalent per kilowatt-hour primary energy, while the German government considers it is 0.39. In the Dutch case, that leads us to 14 tons CO2, and in the German one to 377 tons. What about the annual electricity bill? Well, with a price of 30 cents per kilogram, we have to change our scheme a bit and multiply it by the number of kilograms of wood pellets used, which is 215 tons. The annual energy costs are therefore 64,500 euros. And what about the investment costs? We saw that a nominal load of 421 kilowatt is enough for both hot tap water and space heating. The investment costs of a wood pellet boiler were said to be 240 euro per kilowatt, which brings us to a total investment of 421 times 240, which is 1,040 euro. Finally, the service life of a boiler is 15 years, so the annual equivalent investment costs are 1,140 divided by 15, which is 6,736 euro, by which the total energy costs amount 71,236 euro. So, to conclude, with this condensing wood pellet combi boiler, the building has a primary energy consumption of 9,683 megawatt-hour, emits 14 to 377 tons CO2 yearly, depending on the choices made by the government, and the annual energy costs are a bit more than 71,236 euros. Be aware that we did not consider investments in storage space for the wood pellets. This table shows the summary of the performances. There are large differences in the estimates of the CO2 emissions of wood pellets. In the Netherlands, it is currently considered that most of wood pellets would come from waste wood or sustainably managed forests, while our German neighbors consider that waste wood would never be enough for large-scale heating and would lead to deforestation, in which they are surely right. The electrical boiler performs badly, except when it comes to its low price. However, the high electricity price and its huge electricity consumption makes it financially not interesting in the end. Of course, the poor environmental performances would improve tremendously if the electricity was generated by renewables. Thank you for your attention. I hope you have enjoyed this way of comparing energy supply options. Goodbye.